Okay, today let's continue the discussion about residue theorem. Okay, so in the residue theorem, function is not simply analytic. It may have isolated singularities. So f is analytic in the region G with isolated singularities. A1, AN. Okay, several singularities. Those points are still considered inside the region G. Okay, and you have a gamma. And then this closed rectifiable curve gamma is homologous to 0. And also this closed rectifiable curve gamma does not pass through those singularities. Okay, so first of all, the curve does not pass through the singularities. And second, the gamma is homologous to 0. Homologous to 0, remember that it means the one-in number with respect to the outside points is always the 0. Okay? And then the integral of f along gamma is equal to the sigma one-in number with respect to ak and times the residue function with respect to ak. Okay, so this is a residue theorem. The residue theorem. And if the function is completely analytic without a singularity, so the residue part, you can consider the residue part will be 0. If the residue part is 0, then this is 0. That's a Cauchy theorem. So residue theorem is can be considered as a generalization of a Cauchy theorem. Okay. Cauchy theorem means there's no singularity. The residue means possibly there are singularities. Okay, and because this part you have the residues, the removable singularity has no residue. Residue is 0. The poles have residue. The essential singularity has residue. And after this theorem, so if the one-in number is about the curve, the residue is about the function with together with a point. So the next proposition, or the proposition we discussed last time, was the following: if f has a pole of order m, we want to find a way to compute the singularity, and that g of z be f of z times z minus a to m's power. You cancel that denominator z minus a to m. Order m means the denominator has a z minus a to m. You cancel it. You make this g analytic. Then the residue f with respect to a is, first you take m minus 1's derivative, you evaluate at a, and times 1 over n minus 1 factorial. So this is a way to compute the residue. There's some formula. Okay, so that's everything we possibly need for today's discussion. So today we're going to study some of the example of integral evaluation based on the residue theorem. So the first example is this integral from negative infinity to positive infinity x squared over 1 plus x to 4 dx is equal to pi over root 2. Okay, so we're trying to compute this real integral based on the residue theorem. The residue theorem depends on the singularities, curves, and functions. So here we have function, even though it's a real variable. So we define f of zb, z squared over 1 plus z cubed, z to 4, 1 plus z to 4. Okay, so this is a rational function. This rational function has 4 singularities, 4 poles, simple poles. They are the solutions of a z to 4 equal to negative 1. Okay? They are the solutions of z to 4 equal to negative 1. Negative 1 is e to I pi. Right? Negative 1 is e to I pi. Pi is the argument of a negative number. And then we take the 4th root. Remember, when we take the 4th root, it will be e to I pi over 4. This is 1, or e to I pi plus 2 pi over 4, e to I pi plus 4 pi over 4, and e to I pi plus 6 pi over 4, right? So you just add 2 pi, 2 pi, 2 pi. 2 pi are the 2 pi I are the period. So here I is already in the coefficient part, so you simply add 2 pi. Every time you add 2 pi. If you add 8 pi here, you will go back to e to I pi over 4. So the 4 solutions, the 4 numbers is e to I pi over 4, e to I 3 pi over 4, e to I 5 pi over 4, e to I 7 pi over 4. Okay, so we have 4 solutions. Those 4 solutions, pi over 4 is here, 3 pi over 4 is here, 5 pi over 4 is here, and 7 pi over 4 is here. Okay, they are on the diagonals. Okay, and we can compute the residue. What is the residue of the function? The residue of f with respect to a1. Let's call this as a1. Okay, here. let's use this A instead of W. A1, A2, A3, A4. A1, remember what is the residue theorem? The residue theorem is, the computation for the residue. G of Z is f of Z, Z minus A to mth power. Mth power is just a 1. Here m is a 1, so mth power is 1. And we take zeroth derivative. Zeroth derivative is the evaluation. So the residue is the evaluation of f of Z, Z minus A, evaluate at Z equal to A1. Okay, so okay, so it is we have a Z squared 1 plus Z2 4 and Z minus A1. Z minus A1. Okay, and you do the evaluation at Z equal to A1. Technically, the denominator is Z minus A1, Z minus A2, Z minus A3, Z minus A4, and Z minus A1. Okay. And then you cancel Z minus A1, Z minus A1, then you can do directed evaluation. So you have A1 over A1 minus A2, A1 minus A3, A1 minus A4. So this is the residue. And A1 in this, A2, A3, A4 are these numbers. So you do the computation, EI theta cosine theta plus I sine theta. You have those arguments. Then after simplification, I'm not going to do that. After simplification, you will get this ratio, this complex ratio is, square. This complex ratio is 1 minus I 4 times square root of 2. 1 minus I 4 times square root of 2. Or if you want to write it, it's 1 over 4, the exponential negative pi I over 4. Exponential negative pi over 4. So this is the residue for the first point, A1. And the residue for A2, similarly, you're going to go through the same computation. Okay, so the residue for A2 after computation is negative 1 minus I over 4 times square root of 2. It's 1 over 4 e to negative 3 pi I over 4. Okay, so those stuffs are from the series computation. Let me write it here. It's e I pi over 4 times 2. Here's e I pi over 4 minus e I 3 pi over 4, e I pi over 4 minus 5 pi over 4, e I pi over 4 minus 7 pi over 4. So you do have the series computation. All those numbers we know. This is a simple stuff. It's a 5 pi over 4. You know sine, cosine. They are either they will be plus or minus square root of 2 over 2. All of them will be plus or minus square root of 2 over 2. So it's not that serious to evaluate. Okay. Okay, so we do have those two. We only need those two values because you see how we construct this contour, closed rectifiable contour, and realize the computation. We will not need the residue for the other two poles. Okay. Okay, so far we have a function. We construct this pole, closed rectifiable contour. This is 0, this is R, this is negative R. So we use the upper semi-disk, half disk, upper half disk. We use upper half disk, and in this upper half disk, we are going to let this radius R bigger and bigger. So when R is greater than 1, those two poles are already included in this closed rectifiable curve. What is a closed rectifiable curve? It's the closed rectifiable curve gamma is the interval negative R to positive R union the upper semicircle counterclockwise with positive orientation. Counterclockwise, positive counterclockwise orientation. Okay. Okay, so inside, remember there are only two poles or two isolated singularities. So by the residue theorem, the integral of f, what is f? F is z squared over 1 plus z to 4 dz, 1 over 2 pi I, right? It is equal to, there are only two poles, and also this is a simple curve. The 1D number is just 1, so it's equal to the residue f with respect to A1 plus the residue of f with respect to A2. Only two inside this closed rectifiable curve. Okay, so the residue, check here, you have this residue, and you have this residue. In this step you're going to add them, you cancel the real part, so it's equal to negative I over 2 times the root of 2. The real part are cancelled, you only have the pure imaginary part. Okay, and okay, so the residue along this closed rectifiable curve is this constant, and this closed rectifiable curve has two parts. You can have the part along the R and the negative R and positive R. It's a real number, so it's x squared over 1 plus x to 4 dx. And then along this curve, along this semicircle, upper semicircle, it's called CR. We're going to study one by one what they are. Okay, we will study one by one what they are. And the sum is equal to this. The sum is equal to this. So you multiply, start from here. You multiply this by 2 pi I, you get the integral from negative R to positive R, x squared, x to 4 dx, is equal to, you see this times 2 pi I times negative I is a 1, 2 cancel, it's a pi over root 2, and this one you move it to the right side. So we have this formula. We are going to evaluate by the limit. Remember, we have the we have the improper integral. Improper integral. Regularly, the improper integral from negative infinity to positive infinity. Whenever you see the improper integral, negative infinity to positive infinity, you have to let m approaches positive infinity, n approaches negative infinity, like this, to study it. But if you know this one is already convergent, then you can choose mn to be the same number. You study the symmetric expansion. And this is definitely a convergent improper integral because you just compared with 1 over x squared. Remember that you have the ratio test. You compared with 1 over x squared, you know it is definitely convergent. So we can take the limit, and this is the improper integral. The evaluation of improper integral. Okay. Okay, so we are going to compute the limit behavior along this. This is already constant, so we are going to study the limit of this integral. When we expand this semicircle, what happened for this integral? Okay, so let's continue. This is a circle. CR is Z. Z is equal to R E I theta. Theta is between 0 and pi. Okay, Z is R E I theta. Theta between 0 and pi, upper semicircle. So let's check. Z square over 1 plus Z to 4. It becomes R square E 2I theta plus R to 4E 4I theta, and dz is R I E I theta d theta. Okay, R I E I theta d theta. So in order to have dz, we need the R I E I theta d theta. So here you have R square E 2I theta. So this is IZ d theta. Yes, this is Z, IZ d theta. So IZ d theta. So the dz, let me finish. This is dz over z is I d theta. This is dz over z. I need a copy of z, so this becomes z it's r cubed e 3I theta r to 4 e 4I theta and I d theta. Okay, so dz over z, this is dz over z, is I d theta, and here you put z in the denominator, then it becomes z cubed. Originally z is square, so this is z cubed z to 4. The orientation is from 0 to pi. Okay, yeah, that's it. So okay, so r cubed I, they're constant, so it's a I r cubed integral e 3I theta 1 plus r to 4 e 4I theta 0 to pi d theta. Okay, so that's how we rewrite it in terms of a theta. We are going to compute the behavior when r approaches infinity. Okay, so when r approaches infinity, what is this stuff? And check here, this r to 4 e to 4I theta. This 1 plus this actually measures the distance between the point and -1. Or in other words, you just use let's not use -1. -1 is still inside. Let's use the triangle inequality. It's a greater than or equal to the second number minus the first number. The triangle inequality, not the distance. Okay, this one e to 4I theta up's value is 1, so it's a r to 4 minus 1. Yeah, we can consider as between the distance and this one. 0 is here, negative r is here, r is here, so this is a 1. To get the minimal distance, you just choose r equal to pi, theta equal to pi. This is a minimal distance. It's a minimal distance. Okay. Anyway, just consider this triangle inequality. We consider this triangle inequality. We estimate this quantity. This ops value integral CR z squared 1 plus z to 4 dz. So you put ops value here, put ops value here, and it is equivalent to put ops value here. Now I has ops value 1, so you have r cubed ops value integral 0 to pi e 3I theta over 1 plus r to 4 e 4I theta d theta. Okay, and then you put the ops value into the integral, you get it less than or equal to. Okay, and numerator is the 1. Denominator, we're going to choose less than or equal to, so denominator should be greater than or equal to. Right? So just here you use this. And this is constant, so the integral of constant means this constant number times a pi length. So it's equal to r cubed r over r to 4 minus 1 times pi. Okay, so this is an estimation. The ops value is always less than or equal to this. This one approaches 0 as r approaches infinity, because the denominator has power 4 and numerator has power 3. Okay, so when we take the limit here, the left hand side becomes integral. The right hand side is a pi over root 2 minus this limit. The limit is 0. So finish it. Right? So this is our first complete computation. In this computation, we highly we highly depend on this geometric construction of this semicircle. The upper semicircle, we can rewrite this in terms of theta, and then we estimate the values. Okay, in the next part of the video, we will continue do another computation. Okay, I will stop this video and I start another video.